Welcome to this new lecture on Statics ME 106, and today we're going to start our discussion about chapter number 10, which is about the second moment of area and moment of inertia. So, we have studied in chapter number 9 about the centroid, and we have developed these kind of integrals, if you remember. So the formulation of centroid, the x coordinate of the centroid was, if you remember, it was integral x tilde dA. If we are solving a two-dimensional problem, then it would be dA upon integral dA. So if you look at this integral in the numerator, it is basically the same as here. So these integrals we have already developed in chapter number 9 and we have solved them. And these integrals are basically known as first moment of areas, because if you remember, this very equation was formed after summing the moments. Okay, so these integrals are known as the first moment of area, and we have developed them and solved them in chapter number 9. So if you compare these integrals, okay, shown here, if you compare these integrals with these integrals that we developed in chapter number 9, you will see that now there is a square term. Okay, so x square dA and integral of y square dA, and so these integrals, since they have a square power on y, these integrals in mechanics are known as second moment of areas. So there is a difference between second moment of area and first moment of area. Okay, first moment of area are integrals of this type, integral x dA or integral y dA, and they are used in calculation of centroid. Okay, for areas and volumes. And if you look at the second moment of area, then you see this integral is also very important, and it appears in many subjects like fluid mechanics, machine design, solid mechanics. These integrals will keep on appearing, and so they are given a special name, second moment of area, and a special symbol, that is I, and you can write in subscript x and y. So these are known as the second moment of areas, where Ix is the second moment of area of cross section about the x-axis, and Iy is the second moment of area of cross section about the y-axis. So since these are also integrals, and if you remember, we solved these integrals, the first moment of areas, in chapter number 9 by using strip, rectangular strip. So very similarly, we will going to solve these integrals, the second moment of areas, by using strip method. And for composite shapes, we will going to convert the integration sign into a summation sign. So we can convert integration sign into summation sign when we will be dealing with the composite shapes in chapter number 10 as well. So this is the same strategy that we have adopted in chapter number 9, and we are using it in chapter number 10 as well. Now, the physical concept behind the second moment of area. What is the physical concept behind the second moment of area? So basically, you see that the second moment of area is actually the ability of a cross section to resist bending, or I would say wrapping of the cross section about a particular axis. So it is the ability by virtue of the cross-sectional area or the shape of the cross-section. By virtue of the shape of the cross-section, a structural member will going to resist bending about a given cross-section, a given axis. This is actually second moment of area. So higher the second moment of area, higher will be the resistance uh, offered to bending. So for example, you see that if you have this kind of a beam, and this is a beam is a structural member, okay, and this property of second moment of area is not just only applicable for beams, it is applicable of shafts, it is applicable for columns, it is applicable for axles, beams, even in fluid mechanics, machine design, connecting rods, etc., etc. So this concept is utilized in uh, many areas, the second moment of area. More importantly, it is used in the design of beams. So in order to study the strength and deflection of structural elements like beams, columns, and shafts, it is important to evaluate these kind of integrals, which are known as second moment of area. So suppose that you have a beam here, okay, you have a beam here, and some kind of an external load is acting on the beam, and these are the supports. So of course, you will going to consider that this load will going to deform this beam, will going to deform this beam, okay. And suppose that the beam has a cross sectional area given by this shape I, right? So this is a cross sectional area, or the shape of the cross section of this beam, and some kind of a load is acting on the beam, okay. So this load is acting on the beam, it is the same load. Now under the action of this load, so if you consider this is the horizontal axis x, and this is the vertical axis y, and this load is actually acting on the y axis. So if you look this cross section, this I cross section from this angle, the horizontal cross section, the horizontal axis x is like this. So you see that what is happening, this load, this external load is trying to bend this beam, okay, or trying to wrap this cross section about the horizontal axis. So this edge is actually wrapping up and trying to meet this edge. This is what actually happening here, you see. So the beam is basically bending under the action of the applied load, and if this bending and this deformation exceeds certain limits, then the structural member or the beam will going to fail. So second moment of area represents the ability to resist this bending when structural members are acted upon by external loads. So you can realize that it is a very important concept in the uh, world of mechanics, especially solid mechanics and machine design. And so in this course of statics, we will going to learn methods of evaluating these kind of integrals, these second moment of areas, which represents the ability of a given cross section to resist bending about an axis. So it is important for you to note that if you alter the shape of the cross section, if you alter the value of the cross sectional area, okay, and the shape of the cross sectional area, you will alter the second moment of area as well. Okay, it is purely a geometric property that depends upon the cross section. So therefore, as soon as you will going to change uh, the shape of the cross section, or the area of the cross section, this property, the second moment of area, will going to change. So there are efficient cross sections that can be manufactured, which can resist bending more effectively than others. This is the concept. We have to efficiently modify the cross section of structural members so that the value of this integral, the second moment of area, increases. And when it is going to increase, uh, the given structural member will become more resistive against bending. So this is the concept of, or the physical concept of, the second moment of area. Simply, it is the ability of a cross section to resist bending, right? The first moment of areas, integrals of this type, integral x dA, integral y dA, they are just related to the centroid. They have nothing to do with bending. Okay, it is the second moment of area that represents the ability of a cross section to resist bending. So you will be using these kind of integrals in fluid mechanics, machine design, solid mechanics, etc., etc. Therefore, it is important for us to uh, learn the methods by which we can calculate these integrals. And secondly, one more important point is that uh, a structural member will going to bend about a certain axis. Okay, you have to define very clearly that about which axis you are trying to find the second moment of area, about y axis or about x axis. You have to very clearly define this, because you see that this cross section here, okay, if the load is acting like this in the vertical direction, in the y axis, then, as I mentioned before, that this edge will going to wrap and try to meet this edge, and this edge will going to wrap and try to meet this edge about the horizontal axis. Okay, so as you can see here in this diagram, in this figure, so this bending or this wrapping of cross section is basically taking place about the horizontal axis. But suppose that if a load is acting like this on the beam or on the structural element which is under investigation, if the load is acting like this, then this kind of a load will have a tendency to wrap this cross section about the y-axis. Okay, so the bending or wrapping of the cross section will take place about the y-axis. So you have to keep this in mind, that uh, the second moment of area, which is the ability to resist bending, and the bending will going to take place about a certain axis. So you have to define the axis, about which axis you are interested in calculating the second moment of area. So moving on to the next slide, we have a concept of parallel axis theorem. So as I mentioned in the previous slide, that it is clear that second moment of area, which represents the ability of a cross section to resist bending about a given axis, is calculated about a certain axis. Now this axis can be the centroidal axis of the cross sectional area, that is the set of axes that passes from the centroid of the cross sectional area, and on the other hand, this axis can be any other axis as well. So this means that if you have a arbitrary shape body that has a arbitrary shape cross section area like this, uh, so this cross section area will always going to have some centroid. From chapter 9 you know how to calculate the coordinates of the centroid. So this will going to have some centroid, and the set of horizontal and vertical axes that are passing from the centroid will be the centroidal axis. So this cross sectional area will have the ability to bend about its centroidal axis. Okay, and we will going to generate formulas We're going to learn how to calculate this. But in fact, this cross section area will also have the ability to bend about an axis that is not its centroidal axis, but it can be any other axis. Like for example, here an axis x and y are shown, which 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 are basically not the centroidal axis. So this x and this y is a different set of axes, whereas y dash and x dash are the centroidal axis for this arbitrary shape area. So this arbitrary shape area can bend about the centroidal axis as well, and it can bend or wrap about any other axis as well, which are not the centroidal axis. So what is parallel axis theorem then? The parallel axis theorem, as the name suggests, can be utilized in calculating the second moment of area of a cross section about any axis that is parallel to the centroidal axis of the cross section area. So this means that if this y dash and x dash are the centroidal axis of this arbitrary shape cross section area, then we can use the parallel axis theorem to calculate the second moment of area about this axis x, which is parallel, as you can see, uh, to the centroidal axis x dash. Okay, and which is another axis. It is not this x axis is not the centroidal axis, so it is some other axis, but it is parallel to the centroidal axis. Similarly, this y axis is some other axis, but it is parallel to the centroidal y dash axis. So parallel axis theorem can be used to calculate the second moment of area uh, about any axis that is parallel to the centroidal axis of the cross section area. And so this means that this theorem is really very important, because we sometimes needs to calculate the second moment of area about other axes as well, that are not the centroidal axis. So if we look at this, so we're going to develop the expression or the formula of parallel axis theorem now, because it will be used in problems that we will going to solve in future. So let us define an arbitrary shape area like this, and it has a centroid C, and the centroid C has been considered as origin for the centroidal axis x dash and y dash. So x dash and y dash are the centroidal axis. Okay, we can write that x dash and y dash are centroidal axis. Are the centroidal axis. So this is the arbitrary shape area, and it has a centroid C, and from that centroidal axes are passing, which are x dash and y dash, and this set of axes x and y is some other axis that is obviously not the centroidal axis of this area, and they are parallel to x dash and y dash. So according to the formula of second moment of area, that is integral y square dA or integral x square dA, if we define a very small differential element dA, and we say that its centroid lies at y dash and x dash, measured from the centroid C of this area, and we are interested in finding out the second moment of area of this entire cross section, okay, about the x-axis, So from the x-axis we will going to measure the moment arm, okay. So please remember that this y is the moment arm, okay, because remember that we generated these formulas for centroid by summing the moments. So these were the moment arms actually. So this is the moment arm, y and x are the moment arms. So similarly here we are trying to calculate the second moment of area about the x-axis of this differentially small element dA. So this will be dIx equals to the moment arm measured from x-axis to this area, to this differential area. That is dy, so this distance is dy, as you can notice. So dy plus y dash and into dA and square. So this is the general definition of second moment of area. Okay, let me write down here the general expression. We have defined the second moment of area about x-axis like this. So for this very small, differentially small element, the second moment of area about the x-axis will be dix equals to the moment arm measured from the x-axis, which is dy plus y dash whole square dA. Just following this formula, the general formula of second moment of area. So we just open this bracket by using the formula of a plus b whole square. So you just open this bracket using formula of a plus b whole square. So it will be a square plus 2 uh, ab plus b square, okay, and integration sign will going to appear as it is with each and every uh, member of this bracket. Now if you look at this integral alone, okay, then this integral alone here is representing the second moment of area of this entire cross section, okay, because you are integrating, so you are integrating over the area. So this first integral here represents the second moment of area about the x-axis, about the centroidal axis x dash of this area. So this first integral is nothing but the second moment of area of this entire cross section about the centroidal axis x dash, because here we have y dash square and y dash square, and y dash is the moment arm measured from the centroidal axis x dash. So this first integral is actually the value of second moment of area of this entire cross section about its horizontal centroidal axis, that is x dash. So that is why this is I x prime bar. And then if you look at this second integral, this has a value of 0. And why this is 0? Because this integral represents the first moment of area about the centroidal axis y dash. Sorry, first moment of area about the x dash. So first moment of area about the x dash axis. And as you can see that the centroid of this entire cross section is actually the origin of x dash and y dash. Okay, so the centroid of this entire cross sectional area is basically the origin of x dash and y dash. So this integral will be 0 here at this point, because this y dash is 0 here at this point. Okay, if I elaborate this integral, it will be something like this. So as I told you, that first moment of areas are always related to the centroid. So if you take this integral dA in the denominator here, you will see that this becomes the formula for the y coordinate of the centroid of this cross section. And since the centroid is located at the origin of this cross section, this means that this y prime bar is actually 0. And when this is 0, the value of this integral is also 0. So this means that this entire integral vanishes from our formulation because of this argument. Okay, since this centroid is placed at the origin, okay, of x dash and y dash, and therefore y prime bar will be 0 at this point, because this is the origin of the coordinate system x dash and y dash. Therefore that is why this integral becomes 0. And if you integrate dA with respect to the area, you will just get the total area A. So from this integral we get A times dy square, A times dy square, and from this integral we just get simply that this is the second moment of area of this entire cross section about its centroidal horizontal axis x prime, x dash or x prime. Okay. So therefore the second moment of area of this entire cross section about x axis will be equal to this sum. That is, you have to calculate the second moment of area of this cross section about its own centroid, okay, about its own centroid, plus the product of the cross sectional area A, whatever this cross section area is, you have to calculate the value of that A multiplied by the square of the distance between the two parallel axes. So here you see that the perpendicular distance, so this distance was perpendicular. The perpendicular distance between x and x dash, was dy, or is dy actually. So it is dy square. And similarly, Iy will be equal to the second moment of area of this entire cross section about its centroidal y-axis, that is y dash. You have to find the value of this first, plus multiplied by the area of this entire cross section into the square of the distance between the two vertical axes. So you see that this dx is the perpendicular distance between the vertical axis y and y dash. And you please note that these axes are always parallel to each other. This x dash is parallel to x. This y dash is parallel to y. Only then we can use the parallel axis theorem. The two axes has to be exactly parallel to each other, and they must be separated by some kind of a perpendicular distance. So you see, so this is known as the parallel axis theorem. The above equations are known as the parallel axis theorem. So please go through this slide. Here, please again understand that Ix is the second moment of cross-sectional area about the x-axis, this x-axis. Ix prime dash, Ix prime bar is the second moment of cross-sectional area about the centroidal axis x prime, this axis x prime. And luckily, we have formulas available for simple shapes. So for example, if this cross section is a simple shape, for example it's a square or a rectangle like this, then you have formula available for second moment of area about the centroidal axis x, x dash or y dash, x dash or y dash. So you have formula available. Similarly, if this simple shape is a circle, you have a formula available for this. Okay, you have a formula available for calculating Ix bar prime and similarly Iy bar prime. Okay, or maybe you can have a triangular area or a trapezoidal area. So for these kind of uh, simple shapes, you always have a formula available, and that formula you can directly use in place of these two symbols here. And A is the cross-sectional area, dy is the perpendicular distance between the two axes. So this is the parallel axis theorem, a very important expression, and we're going to use it in solving problems. Now the second concept that this chapter is related to is the moment of inertia. So the first thing that we studied, the first concept that we studied was the second moment of area, and the second thing that we want to study today in today's lecture is the moment of inertia. So second moment of area and moment of inertia. Before we study moment of inertia, let's look at the dimensions of this second moment of area. So as I told you that it is purely a geometric property, it will have a dimension of length raised to the power 4. So if you are looking at the SI units of the second moment of area, it will be meter raised to the power 4 SI unit. The dimension is length raised to power 4. It is purely a geometric property. Okay. So what is moment of inertia? So please note that the unit of moment of inertia is kilogram meter square. Kilogram meter square. So you can look at the unit of moment of inertia and you can look at the unit of second moment of area. Both are totally different things. Okay, second moment of area purely depend upon the geometric property of the cross section. It purely depends upon the cross section. It has a unit of meter raised to the power 4, but moment of inertia involves mass as well as geometry. So its unit is kilogram meter square, and it's totally different thing. Sometimes people confuse these two things together: second moment of area and moment of inertia. But you can always check the units if you get confused. So these are two different things. So what is moment of inertia? It is the ability of a body to resist angular acceleration and deceleration when the body is in rotational motion about an axis. Now you see that in design of machines and machine dynamics, there are a lot of machine parts, machine elements that always undergo rotational motion, or they are designed to undergo rotational motion. And so the ability of a body to resist angular acceleration and deceleration about an axis is known as the moment of inertia. Okay. So as you also know that inertia is actually the property of a body by virtue of which it resists motion, change in its motion. So therefore moment of inertia is the resistance to angular acceleration and decelerations by virtue of the distribution of mass and geometry. So it depends, as you can see, it depends upon the distribution of mass and its geometry. So you can realize that there are plenty of motions that can be characterized as rotational motion. Okay, if they are not completely rotatory motion, they can be uh, they can still be characterized as rotational motion or torsional motion. So it is most often used in studying the rotational dynamics and vibration of machine elements and or mechanical structures. So this means that you can use the concept of moment of inertia in designing machine elements and parts that will undergo rotation. For example, this flywheel here is is a part of internal combustion engine, and due to its high moment of inertia, it will going to regulate the power of the power output of the engine. It will try to keep the power output of an engine uniform by virtue of its high value of moment of inertia. And how this high value of moment of inertia is achieved? By the distribution, by efficiently distributing the mass, and by efficiently designing the geometry of this machine part. Similarly, you can see that hollow shafts can transmit more power compared to solid shafts due to high moment of inertia. So hollow shafts, if you see this motor here, you will notice that it has a hollow shaft. This is why, because the hollow shafts, because of their high moment of inertia, are able to transfer more energy, more power compared to the solid shafts, even though if they have the same mass. So this gives us idea that if the mass of a body is located at farther distance from the axis of rotation, okay, then that body will going to have high moment of inertia. You can notice here that some mass has been removed from the middle portion of this flywheel, and most of the mass is located at the outer periphery. This makes its moment of inertia high. Similarly, all the mass of this shaft is confined at the periphery because it is hollow from the center. Similarly, you see that ship's moment of inertia is made higher about the pitching axis in order to encounter large waves. So this is the pitching motion. Okay, it can go up, it can go down like this. This is the pitching motion of the ship. And if very high waves are coming from the front like this, so you this ship can really encounter these high waves and tides because it has a very high moment of inertia about its pitching axis. So it is part of the design of naval architectures and ships and gunships. Higher moment of inertia is also required to make mechanical structures more robust against vibrations. This is true because you see the natural frequency, which is a very important parameter of mechanical structures, actually depends upon the stiffness of your mechanical structure divided by the moment of inertia. Okay. So higher moment of inertia is required to make mechanical structures more robust against vibration. Because you see that if this moment of inertia is increased, the natural frequency of the you can basically alter the natural frequency of your mechanical structure if you increase or decrease the moment of inertia. So you can really alter the natural frequency and take your system away from resonance. Okay. Therefore, it is also this concept of moment of inertia is also used in uh, vibration engineering. So this concept is used in vibration engineering as well. The knowledge of moment of inertia is required to study problems in vibration engineering. So these are few real world examples of how a moment of inertia helps us in designing efficient machine elements and parts. So if you compare the definition of moment of inertia with the second moment of area, only one thing is common, that both of them represent resistance. Second moment of area represents the resistance to bending when a mechanical structure is externally loaded, whereas moment of inertia represents resistance to angular accelerations and decelerations when a body is about to or is rotating or is about to rotate. So you can see the formulation of the second moment of moment of inertia. It is very same symbol is used. Okay, same symbol is used, but we use subscript m to emphasize the fact that this is moment of inertia, not second moment of area. You have to use subscript m, and this is equal to integral r square dm. So that is why I told you that it depends upon the mass as well as geometry. So Im is the moment of inertia of the body, and r is the perpendicular distance of the mass from the axis of rotation. Okay, so if this is the axis of rotation and your body is rotating about this axis, and suppose that the body is this representing a particle mass, and it is rotating about this axis. So the perpendicular distance measured from the axis of rotation to the mass itself is known as r. So integral r square dm. And since you know that this mass, density and volume are actually related to each other, so density is mass over volume, therefore density times volume is equal to this mass dm. Okay, this mass dm. So in place of this dm we can write integral dv. And now if the body is made up of single material, it will going to have a homogeneous density, constant density, uniform density. So you can take this out from the integral sign, and in that case this integration is simply the volume integral, becomes simply the volume integral. So this gives you idea that moment of inertia can only be calculated for volumes. Okay, only for volumes, 3D. Unlike the second moment of area, which was calculated for areas, 2D. The moment of inertia is only valid for volumes, because you see that if you substitute in place of dm rho dv, and if rho becomes constant, that is your material is made up of a single homogeneous material density, then this is just the integration over the volume, or volume integral. So it is only this concept of moment of inertia is only valid for volumes. Okay, whereas the second moment of area was calculated for areas. It was actually the characteristic of the cross section area. Now, as in case of second moment of area, we have a parallel axis theorem defined for moment of inertia as well. A very similar expression, slightly modified, but almost the same. Actually, the analogy is there. So this I subscript g, this ig stands for the moment of inertia of the body about the axis passing through its center of mass. So this ig represents the moment of inertia of a body. For example, this let us take the example of this flywheel, which can be approximated as a disc, circular disc. So this is the center of mass. Okay, if it is made up of a single material, then centroid is the center of mass, and it is also the center of gravity. So the moment of inertia of this disk about its center of mass, which is actually the centroid if the material is constant, if the material is single material, homogeneous material, then this ig represents the second moment, the moment of inertia of this body about its center of mass. And luckily formulas are available for simple shaped bodies, like for example uh, thin rods, circular discs, and rectangular and square plates. Okay, these are simple shapes, simple volumes. Thin cylinder rod or a cylinder, circular disc, or a rectangular or square plate. So these all are simple shaped bodies, and for them formulas are available for uh, moment of inertia. So we can directly use those formulas here in place of ig. Then plus This time we have m. M is the mass of the body in kilogram. And d square, so d is again the perpendicular distance between the two axes. So this is the parallel axis theorem, and it has same kind of formulation as we studied in case of second moment of area. The only difference is that in case of second moment of area, we used to have a here in place of m, and second moment of area about the centroidal axis in place of ig. Okay, so otherwise everything is same. And this actually gives you an impression that, for example, let's say if you want to calculate the moment of inertia of this flywheel about an axis that is located here at this point. Okay, then you must know the moment of inertia of this flywheel about its center of mass first. That is, you must know this value first, and you can use the formulas given in the appendix of your textbook or from some handbooks of mechanical engineering. You can find these kind of formulas. So first of all, you have to calculate the moment of inertia of this flywheel at its center of mass, that is ig. You should know the mass of this entire flywheel, that is m, and then this distance d, the distance between two parallel axes. Okay, the distance between these two parallel axes can be d. So this distance should be perpendicular distance. And you take their product m d square and add to ig, and you get the moment of inertia of the same flywheel about this axis passing from this point O. Notice that this axis that is passing from this point O is again parallel to the centroidal axis, or the axis that is passing from the center of mass. So this brings us to the uh, end of today's lecture. So from next lecture we will going to solve problems from chapter number 10, which will be related to calculation of second moment of area and then finally moment of inertia. So please go through this lecture again thoroughly and carefully until we meet next time. Thank you.